Hello everyone, welcome to Tactica Imperialis and to today's video. Today is going to be the latest in my Tactica Tutorialis science teaching videos. This lesson is going to be sort of related to our previous lesson on electric fields for A-level physics, but rather than do more electricity, we're going to stay within the fields topic and have a look at gravitational fields today. This again comes from a commenter request to cover this topic, and the next lesson that we're going to do is also going to be from one of those requests. So if there is a topic or a lesson you would like me to do in this format, please do let me know via the Premiere chat or the comment section below. What we're going to do today is following a similar format to our electric fields lesson. You do not have to watch that one first, but if you do wish to watch it afterwards, the link will be in the description. What we're going to look at is we're going to look at forces between objects and how that can be used to derive a gravitational field strength from everything from a person to a planet. We're going to look at field lines. We're going to look at gravitational potential energy in a slightly different way to how you'll have done it at GCSE physics. And we're then going to wrap up the lesson by borrowing from a slightly different area of the A-level physics spec and look at orbits and why objects are where they are in terms of, for example, the Earth around the Sun. I think it's a very interesting thing and it ties in nicely with gravitational fields, so we're going to do it here. Without further ado though, let's get started. If you have any questions you want to ask, use the comments, or if you're watching this live, in the Premiere chat, and I will answer them as best I can. So, we're going to start off, just recap a couple of things just to make sure we're all up to speed, and then we're going to dive in. This is A-level physics, gravitational fields. Let's begin. So, to start us off today, I want to do a little bit of revision for all things gravity back at GCSE. Now, if you're a triple science student, this may not be a completely comprehensive list, but this should cover for the absolute basics you're going to need to know as part of this lesson. So, on the board is a very quick, hopefully, task for you. I've asked you to do a little bit of revision, go back through your notes from GCSE if you have to, and have a look and see if you can find or recall the formula for gravitational potential energy, which you do in the energy topic, and also the formula for weight. You'll have probably done this at Key Stage 3 as well as Key Stage 4, but I do want you to know it because it's going to come up very, very soon. When you get that done, there is sort of a bonus question here. Again, it's a number that we're not going to use particularly heavily today, but I think it is useful to know because, again, it's a good piece of revision. And that is the unit and the value of G, where G is gravitational field strength of Earth. If you want to give that, I would like you to give it for me to two significant figures. I know that you can often see it stated to more or less than that, but I'd like it to two significant figures, please, just the two. So, if you need to pause the video to have a go at this, if you haven't done so already, then you've got about 2 minutes to have a go at this. Hopefully you won't need to look back in your notes, you might even need less time than that, but when you've got an answer, unpause the video and we'll come back and go through the answers. Okay, welcome back. Hopefully that wasn't too strenuous for you. Let's go through some answers. So, the first one is gravitational potential energy. Symbol is EP. You may have also used GPE or just written down E, but to keep it separate from kinetic energy, elastic potential energy and all of that, I'm going to write it as E subscript P because that's the typical notation. Now, if you know your bits about weight, this one solves itself because you can use work done. But since we put this one first, the answer you were looking for was mass multiplied by gravity, or the gravitational field strength, multiplied by height h. So if you've got the ground there, and you've got an object sort of being suspended at a height h with a mass of m, its GPE would be mh multiplied by the gravitational field strength G. Now weight is one that causes misconceptions at a very young age, and I understand that very well. But weight, which I'm going to write as a W, but it is a force, so I'm going to write here F equals, because it's a force, is equal to simply mass multiplied by gravity. Weight equals mg. Now, a lot of people, when they're younger, get mass and weight mixed up. Certainly, I've had that with students before. Mass and weight are very often assumed to be the same thing, because we quite often say something weighs 5 kilos. But that's technically not correct because it has a mass of 5 kilos, its weight is 5 kilos multiplied by g, and that's then measured in newtons. But we don't often go around and say, oh, I weigh 500 newtons. You don't do that, do you? So it's one of the things that we sort of engender in society accidentally, so good on us, well done us. But no, weight is not mass, they are different. So your mass would be in kilograms, and your weight will be in newtons because it is a force. Keep those two separate, that's important. But if you did know this, you could have just plugged it into here and said that your height is your distance, so it's work done. It's another way of working that one out. Hopefully that wasn't too bad, and hopefully you've had a go at this little bonus challenge. So, I asked for this to 2 significant figures. So the answer, which I'm going to write up just a little bit, g equals 9.8. And then you've got 2 answers for the unit. Now, I'm going to give you the SI unit first, which is meters per second squared. The other unit you could have had was newtons per kilogram. That's because g, the gravitational field strength, could also be taken as the acceleration due to gravity. So, because of this, you can see that you've got a force divided by a mass gives you g. So I'll just write that here. G equals W over m. You've got a force divided by a mass, which if you apply Newton's second law, which broadly states F equals ma, you say that F is force, therefore A equals g. So gravity is an acceleration. Gravity is not a force. Again, that's something that a lot of people get wrong. Gravity is not a force. Acceleration is gravity. The force is weight. So the units of gravity, meters per second squared. That's the most common one, and that's the one I expect you to use. You may also, if it helps you remember how you work it out, want to write newtons per kilogram. I suggest you don't, because meters per second squared is the SI unit, but they have the same value and they will give you the same number if you plug in correctly. If you want to write this to more significant figures, then the other way you'll often see G written is 9.81. So 9.81 is how I learned it. 9.8 is often how it's taught at Key Stage 3 and 4, but 9.81 is probably what we're going to use as far as we can going forward today. So that's our first activity, just a quick little recap to get you up to speed on the basics of gravity. Now we're going to get started with a little bit of force to work out the gravitational field strength of the planets and of people and how they vary depending on just where you happen to stand. So, now that we've got our basics nailed down, let's have a look at how we generalize weight equals mass times gravity and sort of look on a more macro scale and work out how we get the strength of a gravitational field. After all, weight equals mass times gravity does work, but it's actually very simplified, and the gravitational field, as you will come to see, is not as uniform as you might expect. So, start off, we have a setup very similar to our electric fields lesson. This is going to be our derivation. So I have here an object with mass capital M, and I have a second object of mass lowercase m. If you prefer, you can write them as, say, M1 and M2. I'm going to keep them as one capital, one lowercase, because I think that's clearer. Your notation will vary. It's up to you. And you'll notice here that they are separated by a distance r, but I've not drawn r as being simply the distance from the edge of the object to the edge of the object. You'll notice that the distance r measures from the center of both of these objects. This is important. So you take it as coming from the center of the object, and therefore you can kind of go back to the idea of it being a point mass. They are not point masses, and that will become very obvious as we go along, but you can treat them as though they are point masses concentrated at their centers, at their center of mass, if you will. Obviously, we're looking at this in terms of planets and stars, so this might be the sun, this might be the earth, so you're at the center of the sun, center of the earth, and that is the distance between them. Their centers is r. Now, this is where the crossovers really start coming. So, the force between these two masses, which I'm going to call F subscript G. Now, you don't actually need to write the subscript. I'm going to do that just to be super clear, is related to these by the inverse square law. So, if you were here for last week's lesson, you'll know what this is already. Inverse square law. Now, we looked at this last time out in our previous lesson on electric fields, and what we are saying is that the force is inversely proportional to the square of one of these variables. And the variable that it is inversely proportional to is r, same as with electric fields. So it's proportional to 1 over r squared. However, the force also depends on how large the objects themselves are. So obviously, if you think about the Earth and the Moon, the Earth has a much greater gravity than the Moon does, because if you jump on the Earth, you come back down pretty quickly. If you jump on the Moon, you go a lot higher. So it depends on the masses of the objects that are interacting with each other, whether that's an astronaut and the Moon's surface or the Sun and the Earth. Those two masses both matter. So it is directly proportional to the mass capital M and the mass lowercase m. Exactly how this is derived, you don't need to know. But that is the formula that we start with. We say that the force between the two objects is proportional to the product of their masses divided by the square of the distance between their centres. Now, the next obvious question is, what is this constant of proportionality? Because a proportionality relationship is great, but if we want to do some actual maths, we need the constant of proportionality. And unlike last time where we had pi's and epsilons and all sorts of nonsense, we just have one symbol to write in. And this formula I think I've done on my channel before in some of my old Warhammer videos. So the force between them is equal to big G, big M, little m, all over r squared. Make sure, now some people get a bit lazy with their notation, it is a capital G. Lowercase g is the gravitational field strength. This G right here is known as the gravitational constant. Gravitational constant. I believe it's attributed to, I want to say Einstein, but I could be wrong on that one. Was it Einstein? Einstein did a lot with relativity and gravity, so he might have done it, but I wouldn't want to say with any certainty. And it's just a number. In fact, I know the number off the top of my head. It's given to you in your formula sheet. It is 6.67-ish times 10 to the minus 11. And then it's got some units. I think off the top of my head, it's Newton meters squared per kilogram squared, I think. That is the constant of proportionality. So once you've got your two masses and distance between them, you just stick them into the proportionality relation and multiply them by G to get the gravitational force between the two objects. And you note I'm not saying the force of gravity. I'm being quite careful not to say that. So I'm going to rub that number off in a moment, but I'm going to give you a second now to take those notes down, pause the video and give yourself a bit of time to take the notes and then unpause and come straight back. Excellent, good work. Now I'm going to rub this bit off and we're going to need to call back to what we did at the start of the lesson. So if I've got a force and I've got a mass of an object being attracted, say, to the planet by the gravitational force, I can use that to work out the gravitational field strength. So if I want to work out the field strength of, let's say, big M, because we're going to treat this, say, like the sun and the earth. So what is the force from the sun that's holding the earth in place? And therefore, what is the field strength of the sun? Well, simply enough, we need to say what we did from the starter. We know that F is mass times gravity, where G is, as I said earlier, the gravitational field strength. Therefore, we just need to do G equals F over m, simple enough, and that leads to the gravitational field strength for a given object is gravitational constant multiplied by the mass of the object itself that is creating the field, not the object in the field, the object itself, so the sun, the earth, your own body if you like. The mass of the object creating the field divided by the square of the radius from that object. So if I had a point object, it would just be the distance away. However, if I had, say, the Earth, the gravitational field strength in terms of R is measured from the center. So when you're on the surface of the Earth, your value for R would be that. You do not say, I'm on the surface of the Earth, therefore the strength of gravity is 0. That would be A, mathematically weird, because then you'd have negative gravity inside the planet, and B, utterly weird, because if there was no gravitational field strength, you'd never come back down when you jumped. So that means that if I was, say, here, at this distance, my value for R would be that. And if you go on to university, you'll see this done, where you can work out whether objects are inside one another in terms of their spherical distance. There's a lot of clever maths you can do with this, sort of working out the densities and all of that stuff, but you don't need to know that. What you need is what is on the board. So you should already have the formula for force down if you don't take it down, and using this formula from the starter, rearrange to give yourself the value for the gravitational field strength. I'll let you take that down now. Excellent, well done. Now, one last thing before we end this segment, and that is about getting into vectors, because I've been a bit lax in a couple of my lessons with vectors and scalars, and I've been a little bit polite. So, if you, particularly are an A-level maths student, you will probably have run across vectors already. And vectors essentially are things that have a size and a direction. So mass is a scalar because it doesn't have a direction, it just has a size. Whereas force is a vector. And one of the rules about scalars and vectors is that you have to multiply. So if I've got my force F as a vector, and it's equal to mg, two scalars multiplied together cannot make a vector. You have to have a vector on both sides in order to create a vector at the end. So the gravitational field strength is also, I shouldn't have put that line there, I'll put it underneath. G is a vector. So if we're being technical and we're doing this in full, if you're doing this vectorially, you should say that the vector g is equal to gm over r cubed r vector, because r vector is equivalent to r times, I'm going to call it r hat, which is sort of the unitary vector in the r direction, in the radial direction, because this is, like our electric fields, a radial field. It spreads outwards from a central point. So, if we're being technical, that's its vectorial notation. The r cubed looks weird until you realise that this modulus of the r vector is there, because that's basically equivalent to r itself. So you might say that that's just gm over r squared r hat. It's another way of putting it. But in vector form, that's that, and you'll definitely need to get a little bit of practice at using that, I think. Certainly if you're wanting to take this any further than A-level. It might even be on the A-level specs these days. I haven't taught this part of the course, and getting access to a specification book at this time is a little bit tricky. So we're going to do one little exercise to test your understanding and make sure that you can do everything that I'm asking you to do. So the exercise I'd like you to have a go at, just to make sure you're comfortable using this formula, is going to go as follows. We're going to use some real-world astronomical data to work this one out. So, the Earth, which has a mass of 6 times 10 to the power of 24 kilograms, I know, it's big numbers, but this is on your formula sheet, as I recall, is a distance of, now you might know this if you're a bit of an astro nerd like me, as 1 astronomical unit, but in SI units it is 1.5 times 10 to the 11 meters from the sun, which has a mass of big M. A bit clearer for you. Big M equals 2 times 10 to the power of 30 kilograms. So A, what is the force on the Earth? And B, what is the sun's gravitational field strength? That's not how you spell strength, Tactica. So, those are the 2 little questions I want to do for you to test your understanding of using those formulas. So you've got your masses, you've got your radius. You need to just scroll back through the video if you need to get your gravitational constant, that you should have written it down in your notes. Have a go at this. I think you'll probably need about 3 to 5 minutes just to plug some numbers in. So pause the video, we'll come back and we'll go through the solutions. Okay, so hopefully you've had a go at that. Hope it wasn't too taxing, seeing as you had all the numbers given to you. It was just a case of plugging in. If you got some slightly wonky numbers, don't worry, we will address them now. So, I've just written down in shorthand all the numbers that you're going to need. Big M, little m, R, and big G. I've not written the unit for big G, it's on your formula sheet, so just copy it off there. Most of the time is good habit. And we're going to now stick these in. So, first half of the question asks you to calculate the force from the sun on the Earth. And in order to do that, we need the first formula that we had from today, which is G, big M, little m, all over r squared. Big G, big M, little m, all over r squared. Then it's just a case of plugging these numbers in. And I'm going to do this on screen for you so that you know I'm not just making this number up. 7 times 10 to the minus 11 times 2 times 10 to the 30 times 6 times 10 to the 24. Hopefully you can see what I'm doing. All over square, so 1.5 times 10 to the plus 11, all squared. You can see I've got that there. Press equals. And you get a number of 3.6 times 10 to the 22 newtons. So that's a really big number. That is the force that the sun is exerting on the Earth to keep it where it is. There is another force that's stopping the Earth falling into the sun, and we'll come to that at the end of the lesson. But now we need to work out the gravitational field strength. Don't mind this is a uni thing. Basically, that's the alchemical symbol for the sun, and I feel like being a massive nerd. Now, to work this one out, the gravitational field strength, you had 2 options. You could either have done big G times the mass of the sun all over r squared, because that's the full formula, and if you did that, excellent, good stuff. But for the ease of speed, I'm going to show you the other method, where you just do the force divided by the mass of the Earth. Because if you look at these two side by side, you can see I've just divided by little m to get from there to there, so you could just plug that into there. Again, that comes back to your weight equals mass times gravitational field strength that we had in the starter. So we're going to stick that number in and divide by 6 times 10 to the 24 and press equals and convert to decimal. So you might notice that the answer is very small, equals 0.00, I stopped writing a 6, 0.006 meters per second squared. Now that number looks ridiculous, and you're probably thinking, what? Why is that so small? The sun's got a huge amount of gravity because, you know, it's holding the entire solar system together. And you'd be right, dear viewer. However, bear in mind that this value is at the surface of the Earth almost. On the astronomical scale, you can sort of ignore the radius of the Earth. It's tiny compared to astronomical units. So on the surface of the Earth, that's how strong the sun's gravity is on objects that are there. So on us, that's the gravitational field strength of the sun. So the Earth is pulling us down, if you like, or towards its center with a force equal to your mass times 9.81 meters per second squared. The acceleration into the Earth is 9.8 meters per second squared, and the acceleration out towards the sun is 0.006 meters per second squared. That means that obviously that's a tiny, tiny, tiny number, meaning that we aren't pulled away from the surface of the Earth into the sun. That, of course, is at this distance, so that is actually as a function of r, for being technical. But if you were on the surface of the sun, just a little aside, so on solar surface, G solar is actually, I just looked this up to make sure I wasn't going mad, 239 meters per second squared. So if you were actually on the sun and you weren't roasted, then the sun's gravity is 24 times greater than on the surface of the Earth. Obviously, if you're at the Earth's radius from the center of the sun, it would be even greater. But the sun has got ridiculous gravity. It's just we're so far away from it that we on Earth don't feel that attraction all that strongly because we're tiny. The Earth feels it because it's flipping huge. It's got a mass of 10 to the 24 kilograms, but us weighing, say, 100 kilograms, it's 0.6 against 10-ish. So you don't really notice. So that's a little bit of practice. I hope you got those right. So those are your two answers. 3.6 times 10 to the 22 newtons and 6 times 10 to the minus 3 meters per second squared. So now that we've done that, we're going to do a little bit about field lines very quickly, and then we're going to move on to gravitational potential energy and do that under this slightly more rigorous radial system. Right, so the next section, this will be quite brief compared to our electric field excursion, is to talk about field lines. Now, we're not going to be here very long because when it comes to gravitational fields, things are a little bit simple. So, in case you weren't in our previous lesson, which I need to stop referring to because this lesson is standalone, field lines are drawn with an arrow, something like that, in the direction a mass will move in the field. Now, the sort of generic term I should say here is a unitary mass. So you can sort of say it's 1 kilogram. I'm not going to bother with that because, again, that's sort of getting up to university stuff. But when we draw our field lines, so here's my object. I'm just going to get a bit more space. The field lines are drawn with arrows, and the arrowhead points in the direction that a mass would move were it inside the gravitational field. So we need to now apply a little bit of real-world science and what we see every day to understand which way do objects move in a gravitational field. So let's take, for example, you. You stood or sat at your desk if you're doing your good diligent work, and if you jump, or you get out of your seat and you jump, what's going to happen to you? Well, you go up, but then you come back down again, because the Earth's gravitational field exerts a force on you, which we call weight, and that force pulls you back down to the surface of the Earth. Now, that might make you think, well, therefore, gravity and gravitational fields point down, right? I could understand why you might say that, but we need to be a bit more clear because, bear in mind, we're not working with a flat plane here. We're working with a spherical object. We're working with planets. We're working with all sorts of things, really. And so the concept of down doesn't really
apply here. So what we need to think about is, if you were able to sort of get a macro view of the entire planet and watch that object move, where would it be moving to? Well, let's say the object was here. Where would it move in the gravitational field? It would move that way. It would move downwards, in air quotes. What if the object was here? It would move downwards, in air quotes, in this direction, and so on, and so forth. Now, if I'm being really technical, I would draw them all the way in. So gravitational field lines are towards the center of the object. And the gravitational field strength, as we've talked about before, is radial. So if that's my object, at this distance I could draw a circle of radius r, and the gravitational field strength there would be uniform, it would be constant. Then if I drew another circle right here, I'm bad at drawing circles, okay? Go with it. Then the gravitational field strength there would be different to there. So the field strength here would be different to here, but it would be the same as here. It would be constant along that radius, that circle, if you like. And always, 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 gravitational fields act toward the center of the object that creates the field. So towards the center of the Earth, the center of the sun, or wherever it so happens to be. That's all we need to say on field lines. So now let's move straight on. If you want to do a quick drawing, you can pause the video and write that key information down. In fact, I'll give you one last sentence. Therefore, lines toward, I can't spell, toward the center. Now, if you had two objects, say the sun and the earth, you can't actually connect the lines together like you could with the electric fields. So you would have, let's say, the sun. It would have its field lines like that. And each of them would have a force on each other, pulling them together, if you like. But you can see here the field lines are not connected like they were before. So just as a side point there. So there's your key notes. Pause the video and take that down. And then we will move on and talk about energy. So the final part of this lesson before we get on to orbits is on gravitational potential energy. I'll warn you now, this requires a little bit of either space magic or really clever mathematics. So stick with me here. The formula at the end is what you need to know, but I'm going to show you how you get there to the best of my knowledge so that it makes a little bit more sense than just pulling it out of nowhere. So there are three formulas at the top of the board, two you've seen today and one you haven't. Gravitational potential energy, force between two objects in a gravitational field, and work done, which I've written as force times distance, where the distance is r because we're working in a radial field. I've then set myself a system up of two objects, big M, little m, separated by a distance r. And the question that we need to work out is what is the gravitational potential energy stored by moving the object to r. Now the way you have to do this is by starting the object off at infinity. So start at r equals infinity, therefore ug equals 0. The reason for that is because if you were an infinite distance between the two objects, then the gravitational field of this would not be affecting this. The force would be 0, and so the energy would also be 0. There would be no energy stored because they're not interacting with each other. You then have to pull m from infinity to r. So from infinity to r. And that actually you'd think would mean I've got to do some work. And you'd be half right. So what we have to do is we pull it in, and that will cause some energy to be either required or transferred. And you'd think, okay, so there's my force. I've pulled it from infinity to r, so it's like infinity minus r or something. That's the distance it's totally moved. Therefore, it gets a little bit messy. But what it does is, because of the fact that this force is attractive, you don't have to do any work in order to pull it in. If anything, you have to do work against this force in order to hold it at a distance r. So you would say that the work equals minus UG, because of the fact that the force is attractive. F. Therefore, UG equals minus F times R, because I've got to hold it at a distance r from the object. The infinity is there mainly just so that you get this sort of limiting factor in play. So it's held at a distance r, so you just times this by r and a negative. Therefore, UG, the gravitational potential energy, is minus GMM over r. Now you might be thinking, Tactica, what are you doing? You've just created negative energy. That's impossible. And you'd kind of be right, but not really, because you don't want to be thinking of this energy in air quotes as being anything other than the work being done to get it there. And that work is being done against the force. So it's in the opposite direction to the force, which is where the negative sign comes from. If you want to think about it in terms of a vector, which you probably should be thinking about it in terms of a vector, this force is in the minus r direction. It's inwards. Remember the field lines from earlier, which means that the energy, which must be positive once you put it into scalar form, when you do the product between force and radius, you have to do a minus r vector times an r vector, which ends up leaving you with that -1. It looks weird, and I understand it's a little bit stupid to see U for energy and a minus sign in the same place. It's odd, it's really odd, but it is a minus sign. And the way I know it's a minus sign, aside from this wibbly-wobbly explanation, is because if you do it using integration from year 13 maths, you will get a negative sign. So that's the formula you need, which I'm going to write a little bit bigger. So U equals minus G MM over R. That is the formula that you need. So write that down. This stuff, this derivation, is kind of supplementary. This bit, probably, you do need. So those two bits you'd need. This stuff, less so. So I'm going to rub this off and give you a chance to pause the video and take it down, the bit that you need. And then we're going to do a little bit of integration, which is going to look like some mathematical magic, in order to explain where that negative sign comes from a little bit more categorically. So, the thing about integration is that it plays a lot with powers, same as differentiation does if you've done that. So you might want to say, and this is something you definitely do a lot later in life, is that UG is the integral of f with respect to r, where you're moving the object from, actually it doesn't matter. We don't need to actually put the limits of infinity and r into place in order to make this work. If we did, then you'd be able to actually, you know what, let's do it. So we're moving it from infinity, so that's our lower limit, to r. from this, which means that you're doing the integral from r to infinity of gmm r to the power minus 2 dr, because it's 1 over r squared, inverse square law, remember? Now with integration and powers, what you do is you raise the power by plus 1, so you add 1 to whatever this number is, and then you divide through by the power you've just got. So that would mean, let's just bring this over here, equals gmm over r to the, this is r to the minus 1, we've added 1, times minus 1, or actually, no, better, divided by minus 1, which creates that minus sign on the front. Put our limits on of r and infinity, which therefore means you've got minus gmm little m 1 over r minus 1 over infinity. That's just 0 because 1 over infinity is always 0. Therefore, you minus gmm over r. You do not need to do it integrally. That is just me showing you why it has to be a minus when you do the full-on mathematics. I showed you that as an aside. It is not a solution you need to know. This is what you need to know. I'll just slide this back across. So that's what you need. Now we're going to do about gravitational potential very, very quickly. I realize now I'm starting to go at 100 miles an hour, and I'm sorry about that, but let's do that. Let's clear this. So, potential, so the gravitational potential is called V, Vg if you like, and it's equal to the energy per unit mass. Now you work it out the same way as you do the energy in terms of maybe doing the integration or moving the object, but instead of doing it with the force, you do it with the gravitational field strength. But this is the quickest way that I can show it to you. Therefore, V equals U over M. So Vg is Ug over M equals minus Gm over R. And these are scalars, so they don't have any of that vectorial stuff to mess with because of the fact that you've got integration and vector products and stuff going on, stuff you don't need to really know, but these are scalars, and Vg, the gravitational potential, not the gravitational potential energy, is minus Gm over R. If you want to put that in terms of G, you can actually do something else. So you might have just seen me, you saw me do that U equals the integral of f dr, and that means that U over M is the integral of f over M dr equals the integral of G dr. Quite clever, no? So therefore, you can express the gravitational field strength equals the differential of the gravitational potential with respect to R. And then that needs to be then separated out into its vector product. So you'd have G as a vector, this would have an R hat over here. Then you have d by dx, d by dy, d by dz. If you know your differentiation and your A-level maths, this will be quite common to you. So you might see gx equals dv by dx. Gy equals dv by dy, etc. That's something you will also see, but that's the main formula, and that's the main formula that you are going to need to take away from this. I appreciate that I've probably just done some mathematical magic that you might have never seen before, because integrals are something that, at least when I was doing A-levels, you didn't do till you're in year 13, and you might not have done this in year 13. You might do this in year 12, depending on how you study your course. So hopefully this stuff we're doing integration has not completely thrown you, I've tried to explain it in terms of physical concepts and then proved it with the mathematics. So that sums up that. That's the whole thing. Hopefully you've had a chance to take that down. If not, rewind the video. You know the drill by now. And so we have one more little cool thing I want to show off just as a last little activity, and that is to do with orbits. So, orbits, well, I'm sure most of you know what an orbit is, and no, it's not one of those mints or sweets or whatever they are. An orbit is when something travels in a trajectory around an object. So, you've got the sun, the Earth travels in an orbit around the sun. Most of us know this. In fact, by the time you get to A-level physics, all of you should know this. The Earth goes round the sun. And there is a formula for that by assuming that the orbit is a circle. Now, the orbit of the Earth is not actually a circle. It's say, oval, an ellipse of some sort. Not an oval, an ellipse is a better word. It's an elliptical orbit. But if we assume a circular orbit, there is a formula for the force is in play. So I'm going to define for you, and this is something you'll meet elsewhere in A-level physics. Centripetal force F equals mv squared over r. So if I have my object going in a circle of radius r, that's its path, and its speed at any given point is v, and it has a mass of m. So you've got mass times its speed squared, or its velocity squared, because technically we need to put it into a, because you've got a square, it goes back into scalar form, we call it the speed at any given point. mv squared over r. I'm not going to derive that here, that's a topic for another time. We might do centripetal force at another time. And centripetal force acts in such a way as to be forwards, if you like. So it's in a straight line from the object. So at this instant, the centripetal force is in that direction because the object is traveling at this instant. In fact, I'll draw it a little bit bigger. So if I have my object here, it's going to travel, it's traveling at the moment upwards. That's the force on it because its circle of its path is like that. So at that point there, it's flat, therefore the force is in a straight line. However, there is a second force when we have orbits in play because we have our object in the middle of mass m. And we know that Fg equals gmm over r squared. And we also know from looking at our field lines earlier that if I just put the big object over here, that force acts in this direction, acting towards the center of the orbit, towards the center of the object creating the field. The field is radial, therefore toward the center of the circle. Now this requires a little bit more of resultant forces to come into play so that you can say, okay, so I've got a force that way and a force that way, so my resultant force is that way. So that's the direction my object's going to move. Then my centripetal force becomes in that direction. My gravitational force is in that direction, so my resultant force is in that direction. And so on, and so on, and so on, and so on. And that is why orbits, at least in theory, are circular. It's really quite clever, and I really like it as a concept. You've got your centripetal force, your gravitational force, and that resultant force bends the object round in that circular path. So if you have a circular path, you can actually work out the radius. So r equals what? So how far is our object from the source of the field? How far is the Earth from the sun, if you like? Well, if you have a circular orbit, I'm going to need to bear with me here. If we've got a circular orbit, then the forces are perfectly equal to each other because the object is not sliding towards or being pulled outwards away from the, say, the sun in this instance. It's staying at an exact same distance all the time. That means the radius isn't changing. We know the masses aren't changing because they're right there. So therefore, this force can't change, which means that this force also can't be changing because they're balanced with each other. So we set them equal to each other so that Gmm over r squared equals mv squared over r. Okay? You might need to just wrap your head for a second around that one. But if I do that, I can then rearrange this equation to solve for r. So these two cancel out. I've got r up there, so times by r squared over here to put an r squared up there. Cross that out, cross that out. Therefore, r equals Gm over v squared. That's something that you can derive for yourself. And if I'm wrong, well, I don't think I'm wrong, but feel free to yell at me if I'm wrong about that. But you can actually work out the distance at which an object is orbiting another object based on if you know how fast it's going, which you can work out because you know how long it takes the Earth to go around its circle of its orbit, and you know the radius of it. Well, you do know the radius of its orbit because of the fact that it's, well, one astronomical unit. We talked about it earlier. But if you can work out the speed of the Earth's orbit around the sun, say if you know its circumference or something like that, you can actually work out that, or you can go the other way, which is the more common thing to do. I'll just rub that out a touch. And instead of solving for r, you solve for v. So how fast is the Earth going around the sun? Well, let's do it, actually. We'll make that our last activity. Let's actually do it. So, the final challenge then for you today, how fast does the Earth orbit the sun? I'll remind you, radius 1.5 times 10 to the 11 meters, mass of the sun 2 times 10 to the 30 kilograms, mass of the Earth 6 times 10 to the 24, big G 6.67 times 10 to the minus 11. So, to solve this, pause the video, 5 minutes, and have a go. Okay, welcome back. Let's have a go then. So, first thing, we need to say that Gmm over r squared equals mv squared over r. Set them equal to each other. Little m cancels out. Times this r across. That gets rid of that r squared. Therefore, v equals the square root of G big M over r equals square root of 2 times 10 to the 30 times 6.67 times 10 to the minus 11 all over 1.5 times 10 to the 11. And I'm not going to actually, okay, I will stick it in my calculator because I'm feeling nice. Square root of 2 times 10 to the 30 times 6.67 times 10 to the minus 11 all over 1.5 times 10 to the 11. And we get a final speed of v is 29,822 meters per second. Good stuff. Right, that is going to be all for today. We've done today about gravitational fields, field strength, field lines, and the potentials within them, as well as a little section all about orbits. I do hope you found this useful, and I do hope you found this interesting, and I hope you took something away from it. If you have any topics you would like me to suggest to do in the future for a lesson, do let me know via the comments in the bit below the video. You know where it is by now, I think. And if you have any questions you want to ask, then the live chat might still be open for a little bit longer, as well as the comments. Thank you very much for watching. This has been Tactica Imperialis, and this has been A-level physics, gravitational fields, with a little aside on orbits. Thank you very much for watching, and goodbye.